I mean, a lot of this is review with some new stuff sprinkled in and language and notation. So we need to make sure that we kind of are putting what we know together with what we are learning, the new stuff. So what we are talking about today is we're talking about rate of change. Now, so far, we've really only focused on linear functions. So the graph of linear functions are lines. And if we refer to the rate of change of a linear function, that's our change of y over change of x, which is also known as what? The slope. Good. Now, for a rate of change, we can have any change in y over any change of x. There's no specifications on what that length for change of x in the denominator needs to be. However, if we are talking about unit rate of change, then that change of x, that difference in the denominator of our input values has to be 1. Hence the name unit rate of change. Okay, so while this is change of y over change of x with any change of x, for unit rate of change, the change of x has to be 1. So for example, why would we need unit rate of change? Well, when you're driving and you're looking at the speed limit, it says like it's 40 miles per hour, right? It doesn't say that it's 80 miles for every 80 miles for every 2 hours. No, they're not making you drive and figure out the speed limit like that. We like our units of measure. So we want to kind of be able to take any information and convert it to a unit rate of measure. So for example, let's look at this first example. Mally walked 3 miles in 4 hours. So if I want to write a ratio representing the rate of travel, right, miles for the time, I want to set up a ratio where I have miles and over hours. So that's my ratio. So given the information, 3 miles for every 4 hours, I can set up 3 miles for every 4 hours. But I don't want to know how many miles she can walk in 4 hours. I want to know how many miles she can walk in 1 hour. So how would I take this ratio and convert it to a unit? I'm going to divide both the numerator and denominator by 4. Now remember, if we do something to the numerator to keep the fraction equivalent, I have to do the same exact thing to the denominator. Because in essence, this is like dividing by 1. Like any number over itself, any number divided by itself is 1. So that is correct. So what is my numerator? It's like 3/4, right? And my denominator is 1. So how many miles does she walk in 1 hour? 3/4 of a mile. Molly walks 3/4 of a mile, and that's fine. Or you can say 0.75, I don't care, in 1 hour. These are word problems, so we write our answer in words with units of measure. So we have to be careful, right? So how many miles can she walk in 9 hours? What could I do? I could take this 3/4. I could convert this 3/4 to 0.75. If it's easier for you to work with decimals, I don't care. So she walks 3/4 of a mile in 1 hour. How many miles does she walk in 9 hours? How would I solve for x? Multiply across the equality sign. So what does that mean? I multiply 0.75 times 9, or 3/4, right? Because that's equivalent. And that's going to equal 1 times x, which is x. So you could either multiply the decimal, or you could say 27/4, do the division, and how many miles does she walk in 9 hours? Yes. That is correct. So we have to answer the question as a sentence, in a sentence. Fair? Okay. Any questions on that word problem? So we had to convert it to a unit rate of change, and then we had to answer the question. Now, here you're given a beautiful table of values, and we want to determine, well, first of all, is it a function? Is this relation of discrete values a function? Yes. How do you know? That's right. There is only one output for every input. So if yes, then I know it's linear, and I can find that constant rate of change. That change of y over change of x, no matter what two pairing of ordered pairs I use. So I could do a difference here over the difference there. I could do the difference here over the difference there. If they're all the same, if the change in y's for consecutive output values over your change of x for consecutive input values, it's constant, it's linear. What is the slope? Is it 1/2 or negative 1/2?
It's negative.
I'm going to look at this one. For starters, 0 minus 2 is what? 0 minus 2 is what? Negative 2. 1 minus 5 is what? Negative 4. Change of y over change of x, negative 2 over negative 4 is positive 1/2. Okay, now to make sure it's linear, you would check all those change of y's over change of x's. So what is the unit rate of change? So if this is my constant rate of change and I want unit rate of change, that means that denominator has to be 1. So what am I doing? I'm dividing by 2. Oh my gosh. So my numerator is 1/2 or 0.5, and my denominator is 1. So if this represents a linear equation, a linear function, I have found my slope, right? But how do I find my b? How do I find the y value of my y-intercept? You could. Yeah, you could. You could. But how would you would just pick these points here?
When x equals 0.
Well, I don't know. I could substitute in a point. That's what I would do. To find b, I would pick any point. What's wrong with that one? Nothing. That one's easy. So when x is 1, y is 0. So what is b? Negative what? Negative 1/2. So I come back in here and I replace the b with negative 1/2. So there's the equation that corresponds to this table of values. Now to plot it, how would you start? Well, you could plot all those points and get the line, but let's make sure that we know how to graph given an equation. So what is the y-intercept? It is a point, 0, negative 1/2. So you'll notice on the quiz, if you didn't write your intercepts as points, you lost points. I will give them to you at the end of class. So there's my y-intercept, and from there I'm going to go up 1 and over 2. And there it is. If you don't label your axes, you also lose points. So that's just kind of reinforcing slope, rate of change, unit rate of change. What happens if you're dealing with a function that is non-linear? Well, slope is your rate of change. Slope is your rate of change for a linear function. So lines, graphs of linear functions have a constant rate of change, and it is the change of y over change of x. Our difference in y values over our difference in x values, consecutive values. However, if we are dealing with a non-linear function, so in this case, if it's not a straight line, it's a non-linear function, well, I don't have a constant rate of change. However, I can find what is known as the average rate of change. I could look for the average rate of change between 2 points. Now notice, depending on what points I choose, the line passing through those 2 points could look very different. And instead of it being a tangent line, which you should remember from geometry, means it touches the curve at one point, we are now dealing with a secant line. So the average rate of change between any 2 points is the secant line, the slope of the secant line passing through those 2 points. So, for example, I could look at the average rate of change between people who are 13 and 18 and get this secant line. But if I looked at the average rate of change, let's say, between this age and this age, it would be a very different secant line. So the slope of those 2 lines would be different. So the 2 points that we are looking for, the slope of that line that passes through those 2 points, are going to have different slopes. So let's look at it in general. Here I have a nonlinear function. If I want to find the average rate of change between these 2 points, I am looking for the slope of that secant line. So you will be given a function, and you will be asked to find the average rate of change between 2 values, 2 points on that curve. Let's go in a little bit more detail and let's talk about that. So let's just go back to this one real quick and let's talk about the slope of this secant line. Let's just be a little bit more specific. The slope of this secant line is my change of y over my change of x. For this specific secant line, I'm using these 2 points. So I have an x and a y value for that point. I have an x and a y value for this point. So let's find it. What would it be for this example? It would be 76 minus what? Over. Okay, so that would be what? 76 minus 57 is 19 over 5. So that is the slope of this secant line. If I were to look at this in general, to find the slope of this secant line, it would be f of x2 minus f of x1 over x2 minus x1, right? That's just function notation for slope, right? This is just slope. But the slope of what line? The secant line. So let's define the average rate of change using function notation, and then we're going to graph it just to make sure we really understand. So the average rate of change of a nonlinear function on this interval, so from x1 to x2, is the slope of the secant line between those 2 points. So I'm defining my points. Point 1 has an x and a y value. So those little subscripts just say, hey, I'm the x and the y value for the first point and the second point. So if I wanted to write the slope of the secant line, slope m, little subscript SEC means I'm looking at the slope of the secant line. Using function notation, it would be the function evaluated at the second point minus the function evaluated at the first point over the change in our x values. Fair? Now, there's another notation that we need to be very familiar with. It's saying that if I say I'm going from one point to another point. So that's my change in x. That change of x, this distance here, I can call h. That is actually your step length. You're taking a step from x1 to x2, and that length is h. So h equals x1, sorry, h equals x1 plus x2. So if I wanted to solve for x2, it would be h minus x1. Fair? That's what this is saying. So I could rewrite these points instead of x1 and x2. I could rewrite these points as point 1 being x1, y1 still, but point 2 would be, instead of x2, I would say x1 plus h. And the output would be the function evaluated at x1 plus h. So I could rewrite this as f of x1 plus h minus f of x1 over x2 is x plus h minus x, which I could simplify the denominator to what? What is that denominator simplified to? Our change in x's, just h. So let's draw that and see if we really understand what that is. There's a nonlinear function. There's my f of x. It's nonlinear. Actually, let me make it a little bit steeper just to make this abundantly clear. No, I don't like that. Yes, I do like that. Do I like that? Oh, it's fine. If this is x1, then this, if f is f of x1, right? That's the y for our first point. If this is x2, then this, oh no, that's terrible. I don't like that graph. Sorry, I'm changing it just a little bit. I want to make sure that this is really clear. That's better. So do you see that this is f of x1? This is f of x2. Does that make sense? This is x1 and has a corresponding y value. So how would I label that point? That point would be x1, f of x1. Fair? That's my input x1. My output is the function evaluated at x1. This point, how would I label that point? Beautiful. Now, the reason I want to show you so many different notations is because you will see it in many different notations. Instead of using x1 and x2, I could call this a. That's my first x. And I could call this a plus h. A plus the step length h. Do you understand that notation? Okay, so then this would be a and then f of a. This would be a plus h, and this would be f of a plus h. So if I'm looking for the difference quotient, the average rate of change, I am looking for the slope of the secant line. So how can I write the slope of the secant line? It's just your change of y, whether I represent it as this minus this, or f of x2 minus f of x1, over my change of x, which is this minus this, which is just h. A plus h minus a is just h. So when we refer to the average rate of change, It is just your slope formula, but you have to understand, number one, it's not the slope of a tangent line, it's the slope of a secant line, and it can change depending on what 2 points where you are on the graph. Right? If I chose these 2 points, the average rate of change is nothing. But we do see that it's changing, but the average rate of change would be nothing because it would be a horizontal line. If I chose these 2 points, the average rate of change, the slope of that secant line would be negative. So it makes a difference on those 2 endpoints for which secant line you're working with. All right, let's try an example. Here's my difference quotient. Again, I can represent these many different ways. But I want to find the average rate of change for this function, and here are my 2 endpoints. So the first thing I need to do is I need to find the function value, this function value evaluated at x1. And then I need to find the function evaluated at that other endpoint, x2. Because if I'm going to substitute into this, I need my outputs at each of those endpoints. So if I take this equation and I substitute in x1, I get -2 times -2 squared plus 1. What would that equal? Okay, so that would be -2 times 4 plus 1, which is -8 plus 1, which is -7. So when x is -2, y is -7. Fair? At that endpoint, at the first point, that's the first point. Now I'm going to do the same thing, but now I'm going to substitute in the second x value that I've been given. Well, let me change that to x2. Do we get -17? So our second point is -3, -17. So what am I really doing? I'm finding the slope of the line passing through these 2 points. That's it. Now, in your heart of hearts from algebra 1, what type of equation is this? It is a quadratic equation. Is the graph going to open up or down for kids? No, a leading coefficient is negative and opening down. We'll talk more about that. But this is a parabola, right? So 2 points on the parabola are here. Yeah? Find me the slope of the secant line passing through those 2 points. You tell me, what is it? The difference quotient is just and from here, I know what my h is. Right? So you could easily find your denominator of your difference quotient just by subtracting x2 minus x1. What is it? Anybody get it? Anybody got it? What? No. What was f of x2? -17 minus f of x1 over h x2 minus x1 is 5. That's not a -3, it's a positive. Oh, this is a +3. Not a -11/5. So the difference quotient is -2. Slope of the secant line passing through those 2 points. Now, what happens in the next example if I don't tell you the 2 points? I have f of x. Well, what else does my difference quotient require? F of x plus h, right? Well, this is just over h. Isn't that my difference quotient? Okay, so I have f of x. That was given to me. That just goes here. But I need f of x plus h. So how can I find f of x plus h? I literally can just substitute in x plus h for x. So what would that be? 6x. So that's 6x plus 6h plus 1 minus f of x, which is 6x plus 1, and that's all over some h. I don't have the endpoint, so I have to just use h. Now, can I combine like terms in the numerator? What do I get? No. One. Yes. And can I simplify that further? 6. So my difference quotient is 6. But what does that represent? That was the slope, right? What type of function is this? Linear. What's the slope of this function? 6. You just proved it. That's kind of cool. No, that's so cool. That's awesome. Okay, so what I want you to do, and I'm going to get your quizzes in just 1 second, but you have a function here. I want you to do the same thing to this function. So you're going to find the difference quotient. To do that, you need f of x plus h. So you will do that. In the next one, you have another function. You need to find f of x plus h, right? And then find the difference quotient. And then I want you to try this one and see if you can find the difference quotient for that one. And you're going to do those now as I get your quizzes. So that is what I want you to do. We will go over those in detail on Monday in class. So we will review the difference quotient. But in the meantime, I'm going to get your quizzes so you can see those.